Morning. So let's kind of recap what we talked about last time. We talked about the addition rule. So probability of A union B is the same as the probability of A plus the probability of B minus the probability of A intersection B. So this is something we talked about last time, and we gave a bunch of examples of it. And then we went over different ways of calculating probabilities, and you got a good sense of how this addition rule works. Then we started off with, then we talked about disjoint events for which the intersection is empty. So probability of A intersection B, if it's 0, then events A and B are disjoint, or equivalently, A intersection B is the empty set. So we take the probability of A intersection B, then probability of the empty set, which is 0. So these two could be used as definitions for finding out whether two events are disjoint. Then we started talking about conditional probability. So we talked about probability that somebody from the general population play in the NBA. That probability is pretty small, right? Very small. Very much, right? But if we have additional information that probability that somebody plays in the NBA, given that person is taller than 6 foot 6 inches, then that probably goes sharply higher compared to this value. Okay, doesn't necessarily mean that if you're over 6 feet 6, you're going to play in the basketball in the NBA. However, your chances of playing in the NBA, given that you are over 6 feet 6 inches tall, goes higher significantly. And similarly, we talked about probability of somebody getting cold, or actually somebody getting the flu. Okay, somebody getting the flu versus probability of somebody getting the flu, given that is the winter season, or W. So conditional probabilities change things in a meaningful way. Okay. So it is very important for us to understand conditional probability. And then I gave examples like a probability that the email you receive is spam, given that it has certain words like sale, promotion, or buy, etc. So given the presence of these words, or some of these words, what is the probability that the email that you receive is a spam? And then based on this, you calculate a probability. So let's say if this probability is 70% or 0.70, then you'll go ahead and categorize this email as spam, and you'll put it into the spam folder. On the other hand, if it's less than 0.7, okay, or 0.70, in that case, you're going to put it in the regular inbox category. So this is something that's being done and used in the real world. So these are nothing but straightforward applications of conditional probability. Now, what I'm going to do, I'm going to talk about, actually a bit of a notation. Probability of event A, given that this vertical line is given that event B has happened. Given that event B has happened. What is the probability of event A happening, given that B has already happened? What is the probability of somebody playing in the NBA, given that we found out that the person is over 6 feet 6 inches tall, or over 6.5 feet tall. So given this information, this changes itself. Okay, the probability of playing in the NBA. So there are many, many real world scenarios where given certain condition, the probability of the event that we are looking for changes in a meaningful way. So conditional probability is kind of important. I would say very important rather for us to study. Having said that, let's go ahead and talk about probability of A and B. So let's see where are we in the notes. So conditional probability. Okay, so let's go ahead and define these things first, and then we'll talk about it. Okay, so I'll actually write it out here. Probability of A and B. So probability of A and B, probability of A and B, right? We define it to be probability of A times the probability of B, given that event A has already happened. That's how we define probability of A and B. But remember, A intersection B is the same as the B intersection A, correct? So think of two events. Okay, this is your A and B. A intersection B is this region, the overlapping region, A intersection B. But this is the, by the way, same thing as B intersection A, right? So order really doesn't matter. So order really doesn't matter. So A intersection B is equal to B intersection A. So think A intersection B, which is the shaded region, is the same as B intersection A. So we could say probability of A intersection B is the same as the probability of B intersection A, because in essence, we are referring to the same region. Now, which is to say that I could put it as these two things are going to be equal. Probability of B intersection A, probability of B intersection A is probability of B times the probability of A, given that B has already happened. So now look, it's very important for you to understand that the order is not important. And we know that these two things are equal. This and this are equal right here, because it refers to the same thing. So in essence, we could say that this thing and this thing are the same. Since the left sides are equal, the right sides must also be equal. So what does it say? Probability of B, the second one I'm writing, times the probability of A, given that B has happened, is the same as the probability of A, the top one, times the probability of B, given that event A has already happened. So now what do? We are assuming that none of these probabilities are zero. So probability of B in particular is not zero. So I'm going to go ahead and divide it by probability of probability of B. So I'm going to divide this by probability of B. So divide by probability of B divided by probability of B, assuming that probability of B is not zero, because division by zero is not allowed. So these and these cancel out. That gives you probability of A given B is equal to probability of A times probability of B given A, which is the numerator, all of it divided by probability of B. Okay. I have done a couple of things here. So let me highlight what I did. So this is one very important result. This is called Bayes theorem. Bayes theorem. And these are actually definitions of intersection. Probability of A intersection B is the probability of A times the probability of B given that A has happened. So this is the conditional probability. Okay. So we introduced the concept of conditional probability in the intersection definition, probability of an intersection definition. So concept of A intersection B. Probability of A intersection B is probability of A times the probability of B given that A. Now, probability of A intersection B is the same as the probability of B intersection A. So we could say probability of B, which is here, times the probability of A given that B has happened. Now, these two things are equal. So I could say that these two things are equal too. And if I equate them, and then divide both of them by probability of B, I get this theorem. This is called Bayes theorem. This is a famous theorem. Bayes theorem is very, very useful. Now, there are two things that I have covered here. One is here I have defined the definition of intersection. So, and slash intersection I have defined here. And here I have the Bayes theorem. Bayes theorem. Now, Bayes theorem is important because in the real world problem, in the real world, it has a lot of application. Sometimes you have one conditional probability. That means you know what is the probability of B given that A has happened, but you want the opposite one. Probability of A given that B has happened. So look at the difference between these two, this and this. The order is reversed. In this case, on the right-hand side, you know the probability given that A has happened. You know that. If you know that, you can actually find the probability of A given that B has happened. In real world, there are many situations where you know one of the conditional probabilities, you want the conditional probability in the other way around. Okay, you know, let's say you know probability of B given A, but you want, so you know this, but probability of A given B, you want this, okay? You want this. So you know this and you want this. So if you know this, then you can go ahead and use this Bayes theorem, and you can go ahead and find this. Oops, let's find this. All right. And typically you have information about probability of A and probability of B. And that is how you do it. Given one thing, you can find something else. Is this clear to everybody? The definition, two things I have defined here in a way. One is the actual definition of intersection, and from that I have rather derived, not defined, but rather derived Bayes theorem. And these are the two topics that I talked about here. Anybody, any question on this?
No question.
No question. Everybody okay? Everybody's all right?
Yes.
Okay, so let's clean it up. And let's see what we got here. So this is exactly what I've got here. Probability of A intersection B is probability of B times probability of A given B, or probability of A intersection B is probability of A times probability of B given A. And then I have went ahead and equated these two and derived Bayes theorem. Observation, note that the order does not matter. Okay, so you can switch A and B's. Order doesn't matter. Why does the order not matter? Because if this is your A intersection B, A intersection B, this is the same as B intersection A. Let's say this is A and this is B. So order doesn't matter. In general, probability of A given B is not equal to, so probability of A given B is not equal to probability of B given A. In general, that is not equal. Probability of A given B is not equal to probability of B given A. Now let's go ahead and talk about the next topic. So let's see. Disjoint and independence. I think I talked about disjoint before, so there is no point of repeating it. So probability of A intersection B is 0. That means these two events are disjoint. Also, we use the term mutually exclusive. Okay, remember, ME, mutually exclusive, to imply disjoint. Independent events. So that's a topic that I haven't covered. And a few of you sent me emails saying that, oh, how do I answer this question? And I told you that wait until today's class. And by the way, I have I extended it, the deadline for the homework, or when is it due? Mm-hmm. Was it due yesterday or is due coming up?
It's due September 30th.
Oh, so we have time. So I thought for some reason it was due yesterday. So two events are independent. So let's say you have two events, A and B. These are two events. Events A and B are independent if probability of A is the same as the probability of A given that B has happened, some other event B. All right. If the occurrence of B does not impact the probability of A, that means we call two events A and B independent. Or we could define it the other way too. Probability of B is the same as the probability of B given that event A has happened. It doesn't matter whether event A has happened or not, the probability of B is not changing, all right? So this is how we define independence. So two events are independent. So probability of A is the same as the probability of A given that some event B has happened. Probability of B is the same as the event probability of B given that some other event A has happened. That's what the definition of two events being independent. So that means if A and B are two different events, one does not influence the outcome / occurrence of other, the probability. One does not influence the probability of the other, okay? Or vice versa. Now, there is one confusion that happens, and I went to the similar experience like you do. I'm nothing special. I'm just an ordinary person like many other people. And I made the same mistake too. Two events are independent does not mean that they are disjoint. Two events are independent does not mean that they are disjoint, okay? Or vice versa. What does that mean? That means if two events are independent, that does not mean that they are gonna be disjoint. Or if they are disjoint, that doesn't necessarily mean that they're gonna be independent. What it says that one does not imply the other. So independence does not imply disjointness, or disjointness does not imply independence. Okay, one does not imply the other. It kind of sounds reasonable from an ordinary perspective, but in reality, it really isn't. Okay. So there are a couple of questions. Let's see. For the homework, that was one of the questions. How do we add the straight slash for the formula? Thank you, LV, for bringing that up. I was going to add this. The answer is you can't. for some reason in the homework, it doesn't allow you to put the vertical line. And this problem, I have been meaning to fix it. I haven't fixed it. So I'll show you how sometime today, how to enter it. And you guys go ahead and enter it that way. All right. So no worries about that. It's kind of weird that it doesn't take the answer on the system. Some odd behavior of technology that's causing you not to be able to put vertical. Okay. Does it answer your question, LV?
Yeah, so how do I put the answer in since it keeps saying I got it wrong?
Okay, I'll show it to you. I'll go to that problem and try to answer it for you. Okay.
Okay, thank you.
I'll show it to everybody. All right. So this is one problem I meant to change, but I should make it a multiple choice. That way you guys are not going to be confused. It doesn't allow you to enter the vertical line. All right, independence versus disjoint. So here is an example. I enjoy this example, giving this example to the students. So let me write it down on the side. Okay. My event A is 2, 4, 6, 2, 4, 6, and event B is 2, 5. Okay, and event C is 3 and 6, and event D is 1 and 4. Now remember, these events are as it relates to rolling a die. If you roll a die, your sample space is labels 1, 2, 3, 4, 5, and 6. If you're rolling a die, your simple events are 1, 2, 3, 4, 5, and 6. In the context of rolling a die, I defined 4 events. Events A, B, C, and D as presented here. Now, A and B, 2 events together, C and D, 2 events together. Then we are going to go ahead and find out whether 2 events A and B, they are independent or not. Then we are going to find out whether they are mutually exclusive or disjoint, or it cannot be determined. So we are going to kind of play around with independence versus mutual exclusiveness / disjointness, or can we not determine? Is the question clear to everybody? In the context of rolling a die, we have defined 4 events, A, B, C, and D as presented here. Now we are going to find out whether the events A and B are independent or not. If 2 events are not independent, they're called dependent, right? Mm-hmm. Then the next thing we are going to find out is whether they're disjoint or not. Okay, let's go ahead and take the background off. So first show that, so events A and B, A and B. In the context of these 2 events, we need to show whether they're disjoint / mutually exclusive. We can show it in a couple of ways. A intersection B, if it is non-empty, that means not 0, then they are not disjoint. Whereas if it is empty, it's disjoint. Okay, so let's find A intersection B. A intersection B. What is A intersection B in this context? Can you find it?
2.
2. So what is the probability of A intersection B? There will be the probability of getting a 2, right? When you roll a die. What is the probability of getting a 2 when you roll a die?
1 out of 6.
1 out of 6, perfect. So we just found out probability of A intersection B is 1/6, which is obviously not equal to 0. But remember, two events are independent if the probability of their intersection is 0. So, I mean, not mutually independent, I meant mutually exclusive or disjoint. Probability of the intersection is 0, meaning that events are disjoint, right? But this is not 0. So these two events are what? Not disjoint. Is this part clear to everybody?
Yes.
So this is how you show that two events are disjoint versus not. So these two events are not disjoint. All right, now we're going to talk about independence. So remember, probability, two events A and B are independent if probability of A is the same as the probability of A given that B has happened. Or you can do it the other way. Probability of B is the same as the probability of B given that event A has already happened. Okay? So this is what the definition is. So we are going to show it both ways. Okay? So let's try probability of A. What is the probability of A? What is
Yeah,
it?
6.
It's what?
3 out of 6.
3 out of 6. Yeah, of course. When does A happen? So make sure that you understand the context. When does A happen? A happens when you roll a die and then the outcome is either 2, 4, or 6. Outcome is 2, 4, or 6. Not all three can happen at the same time. Remember, only one of these three can happen, right? If you roll a die, you get a 4, event A has happened. You roll a die, you get a 6, event A has happened. You roll a die, you get a 2, event A has happened. So you need to make sure that you understand what does it mean for event A to happen, okay? So, which is pretty easy, 3 out of 6 or 1/2. So that's probability of A. How about probability of A given that event B has happened? So probability of A. So now this is where you kind of have to think, and sometimes students go kind of crazy about it. I don't get it, I don't get it. Don't overthink, just think simply, all right? Probability of A, okay? Remember, the key thing is after the vertical line, given. Vertical line stands for given. Probability of A, given that event B has happened. So if we know that event B has happened, right?
Mhm.
What does it mean? It's either 2 or what?
2 or more.
5.
2 or 5, right?
Oh,
If event B has happened, that means outcome of rolling a die is either 2 or what?
or 5.
5, right? So now
It's 5.
we know
6.
is what? What is it?
5 out of 6.
5 out of 6, okay. All right.
1 out
Let's
of 6.
1 out of 6. Okay. Any other response? Because I want to see response for this one, everybody. Think about it, everyone. What is it gonna be? Oscar, what do you think?
I would also say 1 out of
1 out of
6.
6 because 2 is also an event A.
Okay. 1 out of 6. Anybody else? Anna Flores, what do you think?
1 out of 6.
The other Anna Martinez, what do you think?
1 out of 6.
Okay.
Wait, could
Yeah.
it be 1/2 because there's only 2 of B and there's only 1 that's in A?
Okay,
Yeah, that's what I was
Adrian,
thinking.
Jasmine. Okay, any other thoughts? Anybody?
Could it be 2 out of 6?
2 out of 6. Noah saying. Mariana, what do you think?
I also think it's 2 out of 6.
Okay, there are 2 Noahs here. Noah Umamoto, what do you think?
He said 1 out of 6 in chat.
He said 1 out of 6 in chat. Okay. Stephanie, what do you think?
I was saying also 1 out of 6, considering that the event of 2 is in both A and B.
Okay. How about Arvin? What do you think?
1 out of 6.
1 out of 6. LV, what do you think?
1 out of 6.
1 out of 6. Okay. Jason and Jasenia, what do you think?
I think it's 1 out of 6.
Okay. Ivan, what do you think? Jason, where are you?
I trust 1 out of 6 too.
You trust. Okay. Jason, Riley, where are you?
Yeah, I'm right here.
Okay, what do you think?
I put 1 out of 6 in chat.
Okay, all right. I think I ran out of tries. All right. So everybody loves 1 out of 6. Jasmine, are you there?
Yeah.
Okay. Then Adrian, are you there? What's
Yeah.
it, Adrian? Adrian, what did you say? 1 out of 6?
I said 2. I said 1 out of 6 and 1/2 because I don't know.
You-
I have 2 different answers.
And
I'm
Jasmine?
curious how people are getting 1 out of 6, but I got 3 out of 6. From what I think, it's like A and B, they have 2, so I'll just cancel that out, and I'll get 4 and 6 and 5. And you roll a die, it's all 6, right? So it's like 3 out of 6. I don't know. That's what I got.
I quite
Like
did not
1/2.
follow your reasoning, Jasmine. Can you repeat that, please?
From A and B, there's
Mhm.
2 in both of those, right?
Yes.
And when you roll a die, the thing is like 6.
There are
So
6
if I
possible
cancel,
outcomes.
yeah, and I take the 2s out, and I'm just left with 4, 6, and 5. So I'm thinking it's 3 over 6 and 1/2. But I'm confused how people are getting 1 out of 6.
Ugh, Jasmine, you almost made me happy, then you disappointed me. I was hoping at least one person would see what is happening. Somebody would see the light. I guess not. All right.
Well, I actually just had a thought about it though, is that if you're saying that A will happen if B has happened, you can't have, because A doesn't have the 5 in it, so you can't have A happen if B hasn't happened.
You could have, if B hasn't happened, then you could have still A happen if you have 4 and 6. If B hasn't happened, we know that for sure 2 has not happened, right? Or 5 has not happened. It could still be 4 and 6, so it could happen. One last chance, everybody. No other volunteers? Okay, all right, I'll go, I'll volunteer myself. So look at this, everybody. Probability of A given that what has happened. What happened, we know for sure. What is given for sure, we know that that has happened 100%. Whatever is given, that is at 100%. That means we know for sure that given thing has happened. Remember that. If you toss a coin, before you toss the coin, probability of getting a head is what? 50%, right? If you toss a coin, before you toss it, what is the probability that you will get a head? It's 50%. But if you toss the coin and you get a head, what is the probability that you will get a head? Then it's not a probability anymore. The event has happened. It's at 100%. But if you toss the coin, you get a tail, it's not a probability anymore. The event has already happened. It's 0% chance or zero. It hasn't happened. Technically, I shouldn't say 0% or 100%, but they're kind of equivalent, but may not sound. If we are talking about tossing a coin, okay, if the event has happened, there is no probability. Probability is associated with an event that hasn't happened. If it has already happened, you don't have a choice. It either happened or it didn't. If it happens, it's at 100% chance, or if it didn't, it's at 0% or it didn't happen. So here we know for sure that B has happened because it's given B has happened, right? We know that for sure. Is everybody okay with me on this?
Yes.
Everyone, do you understand what I'm saying here? We know for sure that this B has happened. This is given. But if B has happened, we know for sure that the outcome is either what? 2 or 5. So now, given that B has happened, what is the chance or what is the probability that A will also happen? If we know that B has happened, we know that it's either 2 or what? 5. Only these two outcomes are possible because we know that B happened already. Now for A to happen also, you have to have 2 happen, right? Not 5. If B happened by rolling a die and getting a 5, then A has not happened, right? If you roll a die, you get a 5, B has happened, but in that case, A will not happen. But if you roll a die, you get a 2, in that case, B happened as well as A happened, right? So probability of A given that B has already happened is what?
1.5.
1 out of 2, because you have 2 items in B and only one could give you A happen, right?
Right.
So that's why it is 1 out of 2. That's exactly what the answer is. Now look here. Look at this. Probability of A is 1/2. Probability of A, given that B has happened, is still 1/2. So these two events are what? Independent. That means it doesn't matter whether B happens or not, the probability of A does not change. Therefore, they are independent. I showed it using this. Now let me show it to you using this. Jasmine,
Yes.
you somehow you got the right answer, but for the wrong reasoning.
Oh my god.
So for a few seconds, I thought, yes, you got it, but then no, you didn't. Now, does everybody know why is it 1/2? Is everybody absolutely clear on this?
I am, yes.
How about the other 35, 36 people?
Wait, do you think you go over it one more time?
Okay. Look, we know that event B has already happened, right? we know for sure that event B has already happened. Why? Because they tell you that event B has happened. Now, when can event B happen? If you roll a die, you get either 2 or you get a 5. Event B happens when you roll a die, you get 2 or you get 5. But you don't know which one has happened, right? All you know that B has happened. You don't know, is it 2 or is it 5? So in that case, your chances of A happening will be 1 out of 2, because out of these two, only if you pick 2, or if the outcome is 2, then A will also happen. But if the outcome is 5, then A will not happen. So your chances of happening A as well as B would be 1, just one number out of these two numbers, or 1/2. Okay, given that B has already happened, the probability that A will happen is 1/2 because of this. Now on the other hand, let's say B had 2, 5, and 6. I'm just making it up. Okay, in that case, what is it gonna be? Probability of, so that, let's say for the sake of argument, don't think that this is the B is this one, but I change the B. What is the probability of A given that B has already happened? Can somebody help me out?
2 out of 3.
Who is talking?
Mariah.
Mariah is correct though. It's 2 out of 3. If we know that B has happened, it's either 2 or 5 or 6, correct? But A will also happen if it is 2 or 6, right? So if it is 2 or 6, A will happen too. So I know that out of these 3, there are 2 numbers that's gonna make A happen. So it's gonna be 2 out of 3. Do you understand it?
Yeah, now I get it. Thanks.
See, that's the tricky part. Now let's go ahead and do it the other way around. I'll give you 2 minutes. Do it the other way around, everybody. Find the probability of B and then find the probability of B given that A has happened. Go ahead and do it. Because I can do it, of course, and I will do it. But I want you to try it on your own. Everybody, try it. All right? So let's go ahead and try it. So what is the probability of B?
2 out of 6.
Let's use green. Yeah, it's 2 out of 6 because there are two items there, or 2 numbers. It's 2 out of 6, which is 1/3. Good. Now let's go ahead and find the probability of event B given that A has happened. So A has already happened. You know that for sure. That's 100%. Meaning that the outcome is either 2 or 4. Okay, hold on. Outcome is 2 or 4 or 6. If B has already happened, if A has already happened, then outcome is either 2, 4, or 6. Now, if we know A has already happened, what are the chances that B will happen? B can happen only if the outcome is 2, not 4 or 6. A has happened by either happening 2 or 4 or 6. But 4 and 6, they do not count. They don't make you B happen. Only 2 makes you B happen. So it's gonna be what?
1/3.
1/3. Now, are they the same?
Yes.
The probability of B is the same as the probability of B given A. Therefore, these 2 events are what?
Independent.
Independent. So you don't have to really do it both ways. You can just do one way and it should be fine. Okay. Now you just saw an example where 2 events are independent, but they are not disjoint, right? 2 events are independent, but they are not disjoint. Now let's look at C and D. Now it should be easy. What is C intersection D, which is what? The empty set. So probability of C intersection D is the probability of the empty set by definition, which is 0. So probability of C intersection D is 0. So these two events are disjoint, okay? Disjoint. By the way, sometimes it might be easier to show that C intersection D is equal to empty set, and sometimes it might be easier to show that the probability of C intersection D is 0. So depending on the scenario, we just use one or the other. You can use either of them as a condition for disjointness or mutual exclusiveness, okay? All right. So next, so these are disjoint, okay? Unlike the last one, not disjoint. So now let's go ahead and do the independence. So probability of C is 2 out of 6. Everybody knows, right? Probability of C, 2 out of 6 is 1/3. What is the probability of C given that D has happened? Now, here is another question of similar type. What is the probability of event C happening given that D has already happened? What is it?
Zero,
Who is talking 0? How do you get 0?
because the event doesn't happen in D.
Exactly. Thank you, Adrian. See, if I know that D has happened, right? That means it will be either 1 or what? 4. If I know that D has already happened, the outcome is either 1 or 4. But either of this outcome doesn't make C happen, right?
Right.
Because C 1 and 4 are not in C. So it's 0 out of 2 or 0. By the way, probability of C is 1/3, but probability of C given D is 0. So probability of C is not equal to probability of C given that D has happened. So they are what? Dependent events. They are not independent, but they are dependent events. Is this clear, everybody?
Yes.
Similarly, if you want to show it the other way around, probability of D, right? First find the probability of D, which is probability of 1 and 4, which is 2 out of 6, which is 1/3. Now, what is the probability of D? Probability of D, given that C has already happened. In that case, what do we get?
So 0.
If I know that C has happened, it's either 3 or what? 6. If I know that C already has happened, D cannot happen because D does not have 3 and 6. So it's 0 out of 2 or 0 out of 6, whatever way you say it, it should be 0 out of 2. So that's 0. So again, probability of D is not equal to probability of D given that event C has happened. So dependent. Now you see a couple of examples where independence and disjointness does not follow or imply the other. An event could be disjoint and not be independent, like the second example, C and D. On the other hand, two events can be not disjoint and still be independent, like A and B. Once again, two events can be disjoint but not independent, like event C and D. Okay, on the other hand, two events can be not disjoint but still be independent, like events A and B. So basically, you want to make sure that you are following the definition properly. Then you'll not go wrong. Are you okay, everyone? I spent good amount of time trying to explain this thing. Any question before I move on?
No questions.
Everybody okay?
Yes.
All right.
So if it's equal, it's disjoint, and then if it's not, it's dependent.
Yes. All right. So we did this example. Now we are going to do something. Okay, so let's go ahead and do this. A box contains 10 black socks and 10 white socks. If you close your eyes and pick socks, then how many socks do you have to pick in order to make sure that you have a pair of the same color? Okay, you have a box with 10 black socks and 10 white socks. So you close your eyes, so they're mixed in a box together, black and white. And you close your eyes and you pick socks randomly. So what is the minimum number of socks you have to pick in order to make sure that you have a pair of the same color? So what do you think? What is the minimum number of socks you have to pick to make sure that you can have a matching pair? By the way, I'll tell you, when I saw this problem for the first time, I made a mistake. Okay, so don't feel bad if you don't get it. 2. Okay, Rodrigo says 2. Quick, respond. Just think about it quickly and respond. Unmute yourself, say it, or put it on the chat.
Wait, what was the question? Sorry.
You read it. I read it already twice. So what is the minimum number?
I would agree with 2.
Who is talking to?
Stephanie.
Okay,
I would say 2.
2. Incorrect. Very simple. If you pick first one, it's black. The second one is white, so it doesn't work, obviously. But if you're lucky enough to get black and black or white and white, then in that case, yeah, it's fine. So 2 is incorrect. One last chance. Rodrigo, 10. I like the answer 10. It should be 11. Anybody else? me being the overthinker, I guess. 4. Jason, no, that's incorrect. 3. 11. Okay. At first, I thought when I saw this problem, I thought it has to be 11. What if you get all of them the same color? Was it 11? That I thought, I think, yeah, I was thinking 10 or 11, something like that. That's wrong. Why? The key here is to recognize that you want a pair of the matching color, right? So let's say you pick the first one is black. All right, out of this box of 20. The second one you pick is a white. Great, no match. But the third one definitely will be a match. Why? If it is black, then black and black matches. If it is white, then white and white matches. So the minimum number of socks you can close your eyes and pick and ensure that you have a matching pair. It doesn't say it has to be black or white. Specifically, it says it has to be a matching pair. You can have a matching pair if you pick at least 3. 2 is not a correct answer, because what if the first one is black, second one is white? That doesn't work. But the third one has to be either black or white. In that case, you will have a matching pair. Is this clear to everybody now?
Yes.
Okay. Next question. Find the probability of picking 3 black socks in a row without replacement. So you pick 3 black socks in a row without replacement. So you have 20 black socks and 20 white socks mixed in a random way in a box. So the probability that you will get 3 black socks in a row. So what is the probability that you will get a black sock the first time? Somebody help me out.
You have a 50-50 chance of pulling a black sock the first time.
Which is what? 10 out of?
10 out of 20.
Perfecto. Next, after you pick the first black sock, what is the probability that next time you will also get a black sock? What is the probability that you will get a black sock next time too?
10 out of 20?
Who is talking?
Elby?
Okay, LB. Why 10 out of 20?
Because there's 10 black socks and then 20 in total.
Are you sure there are 10 black socks? The first one you picked is a black sock, right?
There'd be 9 black socks because you've already pulled one.
There will be 9 black socks because you already took one and put it aside. Out of how many?
19.
19. So these events are dependent. So A, oops, I should not be using, let's call it A1, A2. These are dependent events. So depending on what happens in A, that's going to determine what's happening in, depending on what happens in A1 is going to determine what's going to happen in A2 and whatnot. So what is the probability of getting another? So you got 2 black socks, okay? What is the probability of getting another black sock? That's going to be what?
8 out of 18.
8 out of 18. So the probability of getting 3 black socks in a row is this number, if you multiply them out. Similarly for probability of getting 3 white socks. All right. Next, find the probability of picking 2 black socks and a white sock in a row. So probability of picking the first black is 10 out of 20. Probability of picking the next black is, so black, black, and white is 9 out of 19. And then what is the probability of picking a white sock next?
10 out of 18.
10 out of 18, exactly. And if you multiply these 3 out, that's going to give you the probability of getting black, black, and white. So let's clean it up. So example 2, quality control. As a quality control manager in a clothing company, you randomly select 5 shirts from a collection of 2,000 shirts that just came to your company from Bangladesh. You will reject all the shirts if if you find at least one faulty shirt. It is assumed that there are 20 faulty shirts in the lot of 2000 shirts. Find the probability of accepting this lot. So think of yourself as a quality control manager. So you have a shipment that just came in from Bangladesh. Let's say the shipment is 2000, but in reality, the shipments are like 200,000 or 2 million or 10 million pieces. All right. So I wanted to keep the numbers manageable. So you have a shipment that just came in for 2000 shirts. And then you will randomly select 5 shirts. Even if one of them bad, you're gonna reject it, okay? Even if one of them bad. So in essence, what you want is all the shirts that you pick, 5 of them, has to be good for you to keep the lot. Otherwise, you're gonna reject the lot. So out of 5, so you're a strict manager. Out of 5, you randomly select. Even if there is one bad t-shirt, you're gonna reject the entire lot. So what is the probability of, and from the experience, you know that in a shipment of 2000, there are about 20 bad shirts or 20 bad clothing pieces. So that's from the experience. So given this scenario, what is the probability of getting all five good shirts? Okay, so these are events A1, A2, A3, A4, and A5. These are the events that we are talking about. So A1 is the event that you pick the first t-shirt or first shirt, a good shirt. Similarly, A2, the second one is good. A3, third one is good. A4, fourth one is good. A5, fifth one is good. So now, what is the probability that the first t-shirt will be a good t-shirt? What is it? What is the probability that the first t-shirt is a good t-shirt? Anyone? How many good t-shirts from the experience you had here? 20 are bad. That means how many are good? From experience, you know that in a sample, in a supply of 2000 t-shirts, about 20 t-shirts or shirts are bad. So how many of them are good?
1980.
1980 of them are good, right? So your probability of selecting a good shirt is 1980 out of what? 2000 times. What is the probability that you'll pick the next one and it will still be a good shirt? It's gonna be 19 what? 79?
60.
What did you get? You picked one and that's a good one. You put it aside, right?
Oh, 1. I thought we were subtracting 20. Never mind.
1. So you picked one, that's good. So you put it aside. So then 1979 good ones out of what? 1999. The third one is gonna be 1978 out of 1998 times 1977 out of 1997 times 1976 out of 1996. And if you multiply these numbers, that should be your probability of accepting the entire lot, or probability of not rejecting. Accepting is the same as not rejecting. Is this clear? Do you see how events A, B, C, it's not A, B, events A1, A2, A3, A4, A5 are connected or dependent on each other? So you kind of have to think about these probability problems in a sort of somewhat logical way and have to make sure that it matches. Now, even though we assign numbers to probabilities, don't think that these are like as hard-coded number as 2 plus 3 is equal to 5. In the world of probability, your abstract and very precise concept of mathematics does not apply. So keep that in mind all the time. In the context of probability and statistics, things are more of an approximation. It is not exact. Like if you go to a math class and you say 2 plus 3 is 5, it doesn't matter. It has to be always 2 plus 3 is equal to 5. But in case of a statistics and probability class, these probability numbers that I came up with, that's just an approximation. It could be somewhere, let's say it comes out to, I don't know, 93% chance, all right? So you should not be thinking there is exactly 93% chance. No, there is nothing exact here. It's an approximation, okay? When things are uncertain, you cannot say that, oh, it's gonna be exact. Here, there is no uncertainty in this one, but here there is a lot of uncertainty, okay? A lot of uncertainty. So this is an approximation. Ideally, this would probably be the probability. But what if, you know, in the real world, it turns out that somebody by mistake put a bad t-shirt, just let's say in this lot of 2000, okay? By mistake, somebody put a bad t-shirt at the very last moment on the top of the lot, and the manager happens to pick that one. And let's say, hypothetically speaking, there is only one bad t-shirt in this lot out of 2000 instead of 20, and that happens to be the top one, and the manager picks it. See, then the probability is much higher of being rejected. So think this is sort of like an idealized situation. In reality, if all the t-shirts were randomly selected, then you'd get something around that range, 90-something range. So make sure that you understand the context. It is very important to understand the context. You guys are more used to this kind of calculations than this. First time when I took statistics, I didn't like it. I was like, gosh, things are so not precise. I was so used to seeing precise things, like 2 plus 3 is equal to 5. Here it's not that. But real world is more statistical than this. In the real world, things are more statistical or probabilistic in nature than precise. All right, so that takes care of this guy. Okay. Next example, you have balls A, B, and C. So you have ball A, ball B, and ball C. Okay, so the first one has 10 red, 10 R, 10 black, is it? No, 10 white, 10 white, and 10 red, 10 half red and half white. So C has 5 red and 5 white. All right, good. C has 5 red and 5 white. Now, what is the question asking? The question is asking, if you randomly select a ball, what is the probability that it's a red ball? Okay. You randomly select a ball, very randomly, what is the probability that it's a red ball? Now, this problem kind of has two levels of thinking. All right. One is this. First, so let's take the background off. First, you have to select a ball, right? So there are two events, event A and event B. first you select, oh, I shouldn't call it A and B. Let's call it something else because I used A and B here. So give me a second. Let me change this. Call these events P1 and P2. In event P1, you select one of the three balls, okay? And event P2, once you select a ball, then you select a ball from there. So what do they want? They want probability of, yeah, you select a ball. What is the probability of a red ball? Okay. So red ball. So what is the probability that you select one of the bowls? Okay, one of the bowls. Okay. I should change the word from bowl to boxes because bowl and ball kind of sound similar. So let's say box A, box B, and box C. Okay. So what is the probability that you select one of the three boxes? Is equally likely each box is 1/3. All right. Then once you select a box, then you have to select a ball from there. So probability of selecting first box is 1/3. Now, if you select the first box, okay, what is the probability that you will get a red ball?
10 out of 10.
10 out of 10 or 100%. Good. What is the probability that you select the second box? Is 1/3. What is the probability that you will get a red ball in the second case?
0 out of 10.
0 out of 10. What is the probability that you select the third box? It's 1/3. What is the probability that if you selected the third box, you will get a red ball?
1.5.
5 out of 10. So now this is just 1/3 plus this is just 0 plus this is 1/6, right? 5 goes into 10 twice, 1/6, which is the same as 1/3. I'm going to write it as 2/6. Why am I doing it? You'll see it right now. 1/6 to make the common denominator. This is 1/6. 1/3, I write it as 2/3 because 2 goes into 6 twice. 3 times. That's going to give you 1/3. So that's the same as 3 out of 6, correct? 2 plus 1 is 3. 6 and 6 in the bottom, so it's 1/2. So there is a 50% chance that you'll pick a red ball. There is a 50% chance that you'll pick a red ball if you randomly select a ball from a box. Is it okay?
How did you get 1/6? Was that from multiplying 1/3 times 5/10?
Yes, because 1/3 times 5/10 is what? 1/2. Because 5 goes into 10 twice. 5 goes into 5 once, 5 goes into 10 twice, so it's 1/2. Do you follow it?
Yes.
So 1/3 times 1/2 is 1/6. Next. We're making good progress. So let's see what is next. If a couple has 2 children, but the older one is a boy, this problem, I kind of got it from the internet, honestly. I don't think I get confused myself trying to solve the last one, so I might skip it. If a couple has two children, but the older one is a boy, then what is the probability that they have 2 boys? So these are 2 events, event A and event B. Okay. Sorry, I'm gonna change it. Event A1 and event A2. So the first problem says, if a couple has 2 children, but the older one is a boy. So that's it, the older one is A1, younger one is A2 event. Okay, so older one is a boy, that's for sure. So that's 100%. Then what is the probability that they have 2 boys? So that means for them to have 2 boys, we know that the first one is a boy, then the second one must have to be a boy. What is the probability of second one being a boy? It's 1 what? Out of 2 or 1/2. So the probability of having 2 boys, given that first one is a boy, is 50%. Is this okay, everybody? Probability of having 2 boys, given that the first one is a boy, is 50% or 1/2. That's this question. Now the next one is kind of interesting. Couple has 2 children, but one is a boy. Okay. Couple has 2 children, one is a boy. What is the probability that they have 2 boys? Yes, I want you to think about it. This is kind of a thinker.
1/3.
Who is talking?
Adrian.
Adrian says 1/3. Okay. That's strange number, but I'll take it. Anybody else?
Well, because isn't there a chance that there could be a girl?
I'll explain it in a second. I just want to get more feedback from people. A couple has 2 children. You know that one of them is a boy. What is the chance that they will have 2 boys? Anybody else wants to participate in the conversation? Nobody?
Wouldn't it still be 1/2 because the possibility of the second child being either a boy or a girl?
Okay, Stephanie. Anybody else? All right. The wording is catchy here. That's what's causing you the problem. The answer is 1/3, what Adrian said.
Let's go.
It is so couple has 2 children, but one is a boy. Unlike the other one, it says the older one is a boy. Do you see the difference? It's more of a wording problem. Older one is a boy versus one is a boy. If the older one is boy, that means they are having 2 boys over 2 years, let's say, 2 different years. The first one is a boy for sure. But the second one then will not have any influence because the first one is a boy. If they already have a boy, that does not influence whether they're going to have a boy or a girl next time. So now, in this case, in this one, they say one is a boy. So if they have 2 children, this is what could happen. They could have boy, girl, okay? They could have girl, boy. They could have boy, boy, and they could have girl, girl. That's all that could happen, right? If they are having 2 children, that's all the ordering that's possible. Boy and a girl and a boy and a boy, and a girl and a girl. But they tell you one is a boy. That means this cannot have happened. Just by that piece of information, this kind of excludes girls, girl option. If one is a boy, you cannot have this. So in that case, you're left with these 3. In these 3, this one has 1 boy, this one has 1 boy, and this one has 2 boys. So which one is it? You don't know. It could be any of these 3. Now, out of these 3, we don't want all of them. We want just only one particular one, which is boy, boy. That's 1 out of 3. So if we know that one of them is a boy, the probability of getting a two boys is 1 out of 3. Now the question, one could potentially argue, then what is it, boy, girl, and girl, boy? They could be the same thing if we don't consider order. In that case, the probability becomes 1/2, by the way. So these probability problems sometimes could be argued or seen from a different perspective. So I kind of assume that the order matters, order in which technically it shouldn't matter really. So in that case, if order doesn't matter, then you have really 2 as opposed to 3 choices, that is going to be 1/2. So I'm not going to get too technical about it. It's just for fun. I kind of put these problems for you to think. And the last one is kind of funny. If a couple has 2 children, but one is a boy and he was born on a Friday, then what is the probability that they have 2 boys? So a couple has 2 children, but one is a boy, like this one, and he was born on a Friday. What is the probability that they have 2 boys? So this one, I won't get into it. The logic of this problem is not very clear to me. But apparently the author of these problems, he came up with a logic that shows that born on a particular day could change the probability. Okay. And I one time I did research on this problem, and I thought I understood, but I couldn't convince myself, so I don't talk about it. All right, so ignore this one. So these problems are for fun, okay? So don't take it seriously. It's kind of like something to think about. Okay, next we are going to talk about Bayes' theorem. So we just derived Bayes' theorem, probability of A given B is the probability of A times the probability of B given A divided by probability of B. This is the Bayes theorem. And you can switch the A's and B's, then it's going to switch accordingly. And I have shown you how to derive the Bayes theorem or Bayes formula by using the definition of AND, probability of A and B, right? A and B is the same as the probability of A times probability of B given A, or probability of B intersection A is the same as probability of B times probability of A given that B has happened. Then I make these 2 equal, and of course these 2 are equal. And from these 2, by dividing both sides by probability of B, I get probability of A given B is probability of A times probability of B given A divided by probability of B. And for the first time, if you are seeing it, which pretty much all of you are, I believe, it says it's difficult. Okay, it appears difficult. And so don't get overwhelmed. All right, it'll start to make sense. So this is probably one of the more harder topics that we are going to be talking about, Bayes' theorem, in this class. After that, we have central limit theorem. That's a bit of a thinker. So Bayes' theorem and the central limit theorem, these are the 2 things that I would say is a little bit of harder, on the harder side. It's not hard, but it's on the harder side. So maybe you may want to pay closer attention here. So let's see, what do they say here? In many real world applications, we know probability of B given A, but we need to know probability of A given B. Did you know that in your email spams are separated by using machine learning algorithm that uses Bayes' theorem? Yes. Okay, I mentioned about it. You know, in your Gmail, you have inbox, spam, inbox, promotions, and social. How do they separate it? Using Bayes' theorem. Okay, so make sure that you kind of have a sense of a good sense of Bayes' theorem. And we are going to do some problems. And let's see. Traveling salesman problem. A traveling salesperson stays at hotels A, B, and C 50%, 30%, and 20% of the times, okay, respectively. So a traveling salesperson goes to a city and stays at hotel A, hotel B, and hotel C 50% of the time, 30% of the times, and 20% of the times. All right. When checks in, he has problems with reservation 5% of the times, 10% of the times, and 15% of the times with the hotels A, B, and C respectively. So you may want to pay closer attention. And this problem, I actually got it from an author, Krokoska, his book, Introductory Statistics. Okay, so just have to give him the proper and due respect and credit. So let's go ahead and find the thing. So let's write it out. That way you'll see what's going on. Hotel A. Okay. Hotel A, Hotel B, and Hotel C. He stays 50% of the times in Hotel A, 30% of the times in Hotel B, and 20% of the times in Hotel C. But for Hotel A, 5% of the times there is reservation problem. For Hotel B, 10% of the times there is reservation problem. For Hotel C, 15% of the times there is reservation problem. Okay? Stay and reservation problem. Okay? So these are the two things. So based on this, they want you to answer the following question. So first question, what is it? Find the probability that the salesperson stays at Hotel A and has problem with reservation. So let's define events A, B, and C. Okay? A is the event that the salesperson stays at Hotel A. B is the event that salesperson stays at Hotel B. C is the event that the salesperson stays at Hotel C. Then I defined another event. P is the event that the salesperson has a problem. Okay? P is the event that salesperson has a problem with reservation. Okay? When I say has a problem, I mean problem with reservation. So part A, find the probability that the salesperson stays at Hotel A and has problem with the reservation. So in essence, what I'm asking is this: find the probability that the person stays at Hotel A and has reservation problem. Is this clear to you? Find the probability that the person stays at Hotel A and has reservation problem. So that is gonna be probability of A times the probability of P given A. That's one way of doing it. So I'm gonna do something else here. Let me take the background off. So probability of A intersection P is the same as the probability of A times the probability of P given that A has happened. Okay, I shouldn't have used P. There are too many P's here. No, I'll leave it as it is. Okay, but on the other hand, probability of A intersection P is the same as the probability of P times the probability of A given that P has already happened. Both of these are equivalent definitions. Now, if you go this route, if you go this route, you'll quickly run into problem. What is the probability of having a problem? Okay. Oh, actually, I remember now. The author used R for reservation problem. So let's please use R. My bad here. R for reservation problem. R for reservation problem. R for reservation problem. Probability of R times probability of A given R. So I just changed the P problem to R for reservation problem to avoid the confusion. Is it okay, everybody? Are you guys with me, or I confused you here a little bit? Are you okay?
Yes.
Yes.
Okay, good. So now look, if you go this route, then you run into problem. If you go this route of definition, because probability of reservation, probability of having reservation problem, we don't know. But on the other hand, if you go this route, you're okay. So if I go to this top route, I'm gonna have probability of A and R is the same as the probability of A times probability of R given A. So probability that you stay at hotel A is 50% or 0.5 times probability of having reservation problem if you stay at hotel A. That means given that you stay at hotel A, that's also given 5% of the times 0.05. 5% is 0.05. So it's gonna be 5 times 5 is 25. You have 2 digits after decimal here, 1 digit after decimal, so you have to move it 3 digits. So you put a 0. So okay, this. So probability of staying at hotel A and having a reservation problem is 0.025, or which is, by the way, 2.5% chance of staying at hotel A and reservation problem. Now, what is the probability? What is the next part of the problem? Find the probability that the salesperson has problem with reservation. So let's go back. So find the probability that salesperson has problem with reservation. So in essence, they're asking what is the probability of R. Now here you have to think a little bit. Number one, you can stay at hotel A and have reservation problem. You can stay at hotel B and have reservation problem. You can stay at hotel C and have reservation problem. Is there any other way can you have reservation problems? No. The answer is no. You can stay at hotel A and have reservation problem, stay at hotel B and have reservation problem, stay at hotel C and have reservation problem. That's it. There's nothing more to it. Because since you're staying in 3 hotels, your reservation problems are going to come from these 3 hotels only, from nowhere. So probability of having reservation problem actually boils down to probability of staying at hotel A and having reservation problem plus probability of staying at hotel B and having reservation problem plus probability of staying hotel C and having reservation problem. This is the logical part you have to think. Is everybody clear on this, what I'm trying to do? All right. Now, look, probability of A and R, probability of A and R is 2.5% or 0.025, 0.025 plus probability of B and R, probability of staying at hotel B is 0.3, so 0.3 times probability of having problem if you stay at hotel B is 0.1 plus probability of staying at hotel C is 20% or 0.2 times probability of having problem is 0.15. So if you do the math, you're going to get 0.025 plus 0.03. Okay, 0.3 times 0.1 is 0.03 plus, plus 0.03, also this one. Okay, if you add this up, it comes out to be 0.085. So overall probability of having a reservation problem is 8.5%. Overall, the probability of having a reservation problem is 8.5. Now, the last part of this problem, I'm not going to do it because I'm running out of time. So last part of this problem, I'm going to do it in the next class. Okay, but let me quickly tell you what it is saying. Given that there is a problem, with reservation, then find the probability that the salesperson stays at hotel A. So I kind of want you to think, given that there is a reservation problem. So given that there is a reservation problem, so there's going to be to the right of the vertical line. Given that there was a reservation problem, what is the probability that the person stays at hotel A? Okay, maybe I'll just finish it. Give me 1-2 minutes. Okay, I'll just finish it. So now we are going to use Bayes' theorem. So probability of A given R is equal to probability of A times probability of R given A, all of it divided by probability of R. I just straightforward used the formula. Oops, I erased it, but let's go ahead and do it. I know what is the probability that the person stays at hotel A. So probability of A given R, given that there was a reservation problem, what is the probability that the person stays at hotel A? Probability of hotel A is 50% or 0.5. Probability of reservation problem, given that you stay at hotel A, which is 5%, is given in the problem, in the table, that's 0.05, divided by the probability of reservation, which is 0.085. And if you do the math, you get 0.05 times 0.5 divided by 0.085, which gives you about probability of staying at hotel A, given that there is a reservation problem, is roughly about approximately 29.41% or 0.2941. Okay, roughly about 30% chance that you will stay at hotel A, given that you had some sort of reservation problem. So this is a complete example of where you could use Bayes' theorem. By the way, even though I use this example, but I don't think this is a great example. Oops, I shouldn't say that. This is someone else's problem. In the real world, I think the author gave this example because he or she wanted to clarify the concept. Okay, in the real world, we have other applications that are more useful, things like email or spam classification, or given that you have certain health condition, what are the chances that you will have something else? So it will do some problems like this. Okay, so I want you to go over these class notes. I recorded it, so I'm going to send it to you. And I have given this example, complete example of Bayes' theorem. And thanks to the author of this problem that clarifies all these concepts. Now, then I'm going to take these concepts and apply it to other problems. Okay. So you guys have a wonderful day and rest of the day and tomorrow, and we'll talk on Wednesday.
Thank you, Professor. Have a good day.
Thank you very much.
Thank you.
Bye, have a good day.
Thank you.
Are you gonna show us how to input